Okay, welcome to note set 27, which is covering section 6.5 of the textbook, and the topic is positive definite matrices. So we'll motivate where we're going and what this is all about, and then get into some of the details. So we've been going down this path where we started off with eigenvalues, and we defined what that meant. And we didn't put any constraints on it. We just said the only thing is that A has to be square. So we put no constraints. We said matrix A is square. Are there vectors and values that behave this way? And we called them eigenvectors. Then we said, gee, wouldn't it be nice if we could ensure that the eigenvalues were real valued? Because sometimes that matters. And it's important to be able to ensure that. And we saw that if the matrix was symmetric, then the eigenvalues were real. And we also got some additional mileage out of that. We found out that the eigenvectors were automatically orthonormal, and they would form an orthonormal basis for the whole space. So it is possible to have, oh, there it is. Yep, always, don't know why that comes up, but I know how to get rid of it. So it is possible to get real eigenvalues, but without that orthonormal basis aspect of it. The matrices won't be symmetric. So symmetric gives us actually two things. Gives us ensures the real eigenvalues and gets us the orthonormal basis. So that was nice, and that shows up all over the place in ECE applications. And now we're going to take that a little bit farther. We're going to say, well, we got real eigenvalues, but they could be positive, they could be zero, they could be negative. So even if we limit ourselves to the symmetric matrices, these eigenvalues could be anywhere on the real line. And so now we're going to look at a subclass of symmetric matrices. So we're going to further constrain. So we're going to stick with symmetric and say, but we want those symmetric matrices whose eigenvalues, which are real, are greater than 0. And so why do we care so much about these positive eigenvalues? Well, I know I keep alluding to this, but if I tried to show you all these, where these things actually came into play in ECE stuff, first, we'd have no time to cover it all. Second, you don't really have the background to understand what these applications are. Not even the setup of them. So the problems that engineers solve, that ECE electrical and computer engineers solve, you're not at the point where we can even talk about formulating the problem. So you may be thinking, well, yeah, I can think about ECE problems. I want to design a computer. I want to design an electrical device that does such and such. Okay, those are at the high level. We're talking about once you get down into the how do I make that happen? And we get into the mathematical modeling to ensure that our requirements are being met in electrical circuits and information processing and information transmission. It's hard to describe these problems without any background. So that's why I just keep alluding to, trust me, it's important. We'll see later a little bit in this note set, and we'll see in a later note set how these things show up in some sort of application. So here's our definition. We're defining this new concept called positive definite matrices. Where's my pointer? There we go. They will be symmetric matrices with positive eigenvalues are called positive definite matrices. And we'll see later on why this name makes sense. I mean, it kind of makes sense here from the fact that we've got positive eigenvalues, but why don't we call it positive definite? So that's kind of weird. We'll see why that is in just a little bit. So we're expanding this little Venn diagram that we made before. Remember, we had this big ellipse out here, all real matrices, and technically these should all be square. I didn't include that here. Kind of having a hard time writing that Q there. So technically these should all be square. Okay, I look like a kindergartner trying to write that. Then we go into the next ellipse, which is matrices, again square with all real eigenvalues. So if we look at this, just this ring from here out, that there are at least some of the eigenvalues are complex valued. And we know that they will appear as complex conjugate pairs. Then this next ring in here, all the eigenvalues are real, but the eigenvectors might not be independent, and therefore that excludes the orthonormal case. Then we go into the next ellipse holds symmetric matrices, so eigenvalues are real and the eigenvectors form an orthonormal set. So that's everything, and then inside there. And then the positive definite is inside there. So they are definitely symmetric matrices. They have both of these characteristics, but they are such that the eigenvalues are strictly greater than 0. So none of them could be negative, none of them can be equal to 0. So positive definite matrices, nothing more than symmetric matrices with positive eigenvalues. And these are truly special matrices. They're not rare. In fact, they show up all over the place in electrical and computer engineering and lots of other places, various sciences and other types of engineering. So they're special, but not rare. So we first want to figure out, when do we have one of these? Now, obviously, we could just find all the eigenvalues and check to see if they're all greater than 0. But that takes an awful lot of work, so we'd like to avoid that. You know, we want to find some simpler way to do that. So we want some sort of quick tests. And you know, this often allows us to say at the very beginning of a problem, hey, we know we're going to have a positive definite matrix for this case because, look, this condition is met. So let's take a look at that. So let's just start off with a 2x2 matrix. Here's our favorite, where we've explicitly shown the off-diagonal elements being the same so that we have symmetry. So there's our the one and only two-dimensional real valued or 2x2 real valued symmetric matrix. That's it. And you pick 3 numbers, A, B, and C, and you've nailed down one of those matrices. So when does that matrix have lambda 1 and lambda 2 both greater than 0? And here's a statement. The eigenvalues of A, of this A, are positive if and only if A is greater than 0. So this upper left element has to be greater than 0. And AC minus B squared has to be greater than 0. Well, we've seen that before. That's the determinant. So basically we're saying the upper left corner element has to be positive and the determinant has to be positive. So we're going to prove this only in one direction because this is if and only if, so it goes in both directions. So if the eigenvalues are positive, then these things are true, and that's what we'll prove. And then the other direction, if these things are true, then the eigenvalues are positive. We're not going to do that, but the proof follows pretty similarly to what we are doing. So we're going to assume that the eigenvalues are greater than 0 and then try to show that. So let the two eigenvalues be positive. Then we know that their product will be positive. We know that their product is equal to the determinant of A. So that's a fundamental result that we've already determined. And the determinant of A is just this, so that must be greater than 0. Now, what this tells us, from this we can deduce that either of two cases must exist, right? This thing has to be greater than 0. This number is always positive, but because of the negative sign, that whole term there is going to be negative. So the only way for this thing to be positive, for the whole thing to be positive, is for AC to be positive and be bigger than B squared. That's the key. So AC has to be at least positive, otherwise we have no chance of making this. So if AC is negative, no way can we meet this. So that means both AC must be greater than 0, that's one possibility, or both of them have to be negative. That's the only way we can get two numbers that multiply together that are whose product is positive. Now we also know that the sum of the eigenvalues is the trace. So the sum, lambda 1 plus lambda 2, since they're both positive, that sum must be positive, so the trace, A plus C, must be positive. And that can't be true for this case. So what we've done here is we've shown that this must be true, and we've shown that that can't be true. We're not saying anything about C, we're just simply saying that A, by itself, that's the only thing we really need to say. A must be greater than 0. Yes, it will be true that C must also be greater than 0, but we don't have to check that. All we've got to do is check A and then check the determinant, and we're done. So then A and C are both positive. So if we look at this, and this is the beauty of these theorems, is that it informs us. Don't view them as just stupid, simple, dead pieces of words on a page. They're telling us something. They're giving us a tool. They're giving us a crowbar. They're giving us a lens. How many more analogies can I come up with? So what is this telling us? What about this? What is it telling us about the relationship between AC and B? Well, AC must be bigger than B squared. So B squared comes from the off-diagonal elements. So in some sense, once you fix the diagonal elements, you can't make B too big and have it be positive definite. Because if you fix this already, you pick an A and a C, now there's going to be some limit as to how big you can make B. You can only make B has to be smaller than the square root of AC. So that's kind of cool. And we'll see that idea carries through. So in a sense, we can say positive definite matrices are symmetric matrices where, in some sense, the diagonal elements dominate the off-diagonal elements, in some sense. And for 2 by 2, this is the sense. So here's an example. So this is not positive definite. We check the determinant. Well, first of all, we check the first upper left element. We're good on that. Check the determinant. Oh, ends up being -3. And we can see why it fails. It fails because for this choice of AC, 1 and 1, these are too big. Because we get 1 minus 4, and that ends up becoming negative. So if we were to keep 1 and 1 the same, but knock the off-diagonals down some, if we made them 0.5, this would be positive definite. You can check it. Okay, here's one. It's symmetric, so we could possibly check to see if it's positive definite. Now we see what we've done is instead of decreasing the off-diagonals, we've increased one of the diagonal elements. And now, lo and behold, it is positive definite. So it's not just, that the off-diagonals have to be, small compared to each of the elements. No, but once you've set the elements, there's going to be that product that will set kind of the some sort of limit on the size of these off-diagonal elements. Here's another one. Can't be positive definite. We don't even have to calculate. That's negative, so we're screwed. So here's one. Upper is positive. Well, we know it can't be positive definite because both of those actually have to be positive, but let's go further. So 6, our first check is good. Check the next thing. AC minus B squared turns out to be less than 0. You can check that. So it's 6 plus negative 6 plus 4 ends up being negative. So there's 4 examples. So you can now test any of these 2 by 2s. So what if we go to 3 by 3 symmetric matrices? Well, let's look at the pattern here. So one of the things I'm trying to illustrate with these later notes anyway is not so much the proofs, although we are doing more proofs than we did earlier in the semester, but I'm trying to show how researchers and engineers think, how we generate new ideas. We look at things and we look for patterns and we go, I wonder, could that be the important pattern? And then we poke and we prod and we prove, is it or isn't it? So we're not going to prove this, but it is true. But it could arise by saying, So we go, okay, for two-dimensional matrices, we look at A must be greater than 0. So we're just looking at this here for the moment. A must be greater than 0, and then AC minus B squared must be greater than 0. And so if we think about that for a minute, and this is where the creativity comes, we go, well, look, if I imagine slicing this up into 1-by-1 matrices, if I look at the 1-by-1 matrix in the upper left corner, A is its determinant. Then I look at the whole matrix here for the 2-by-2, and this is its determinant. So we're starting to see a pattern here, and the research side of us, or the discovery side of us, goes, I wonder if I could extend this. Maybe it's a sequence of different determinants that I have to look at. I've got to look at the determinant of this upper left 1-by-1. I've got to look at the determinant of this upper left 2-by-2, and then I have to look at the determinant of the whole thing. And in fact, that's actually it. So we check the determinant of a 1-by-1. We check a determinant of 2-by-2. We had to check two successive things. And then when A is 3-by-3, our intuition pays off. We have to check that that is true. The upper left 1-by-1, the upper left 2-by-2, and the whole thing. And what about larger matrices? Well, we'll see in a minute. I'll write it down. We won't prove it. But you'll see that it's an obvious succession. You just keep going larger and larger from that upper left corner. Can we test for this using pivots? Pivots seem to be an important thing. So again, these are the kinds of questions that someone asks when they're trying to discover things. Engineers are always trying to figure out, how does this thing really work? It's like solving a puzzle. So we've got eigenvalues here. We've got determinants. Pivots are related to determinants in some sense. I wonder if there's a relationship here. And so these kinds of things, this kind of delving into it as engineers usually starts with, I wonder if, and then we try to figure it out. We might try a few cases to see, oh yes, that solidifies the possibility, but it doesn't prove it. And again, we're not going to prove this here, but you can find proofs in books on this. But if we were trying to discover something new, we would need to prove that it really is true in all cases. So if we get an upper triangular matrix from A by going, doing our usual operations, from U we can extract the pivots, and we already know that that process of going to an upper triangular matrix doesn't change the determinant. So in this case, I don't know why I'm saying is equal to 0 here. I don't believe that's correct. We know the determinant of A is equal to the determinant of 0 of U. We also know elimination does not preserve the eigenvalues. We've seen that already. But what we do know is, and this is for the 2-by-2 case, we know that the eigenvalues of a symmetric matrix A are positive if and only if the pivots are positive. So here's the pivots. A must be greater than 0. That's one of the pivots. That's the one number that we never eliminate or change. And then this would be the second pivot that shows up. And you can see how that's related to the determinant for this 2 by 2 case. So for the 2 by 2 case, it's pretty clear that the pivots will tell us also when we have positive eigenvalues. So positive eigenvalues means positive pivots, and vice versa. We essentially showed it here for the 2 by 2 case, but you can generalize it and show it for the general case. So that is a general result. So here is our simple 2 by 2 case, and you can see we've done the elimination. The first pivot is A, the second pivot looks like that. The way we've written it up here is, we have left the A out here and we haven't divided the whole thing by that. So this determinant test shows that both pivots must be positive, so we're good. Okay, so let's set all that aside and we're going to look at a whole new way of defining positive definite matrices. And this really is the fundamental way. We often have multiple ways of getting to an idea, especially when two different things imply each other. So we've been getting to positive definite by defining it to be those matrices for which that are symmetric, for which the eigenvalues are positive. But now we're going to define positive definite matrices a different way and show that that actually then implies that the eigenvalues will be positive. So this is, as I said, the more fundamental way of defining this. If you look in many linear algebra books, they start with positive definite matrices here. So let's start from our eigenvalue, eigenvector requirement. So there's AX is equal to lambda x. We're going to multiply from the left by X transpose. So we're coming from the left here. So we get an X transpose over here. So we're going to have X transpose AX on the left. And on the right, well, we can pass the X transpose through the lambda. And we get lambda X transpose. By now you should start seeing patterns when we start doing these things. And when you see this, you should go, aha! That's the norm, well, norm squared anyway, of the vector. So the right side is a positive lambda times a positive number, right? The norm is positive. And here we're assuming that we have a positive definite matrix. So lambda is positive. So what that tells us, before I go on to that line, what we're seeing here is that at least for eigenvalues, or I'm sorry, at least for eigenvectors, when we put an eigenvector in here, we get this thing out on the right side, and we can show that whenever we put an eigenvector like this, one on each side of A, the result over here will be positive. So this quantity remains positive for eigenvectors. But again, we go, I wonder, could it be positive for all non-zero vectors? We need to make sure that it's non-zero vectors, because if we let x be 0, then this whole thing's going to be equal to 0. So we're looking for let x be anything except for all zeros, and we're wondering, does this thing stay positive always for all non-zero x? Then we would call that matrix positive definite. So we'll write that definition out precisely in just a little bit, but let's see why we're interested in this X transpose AX. So in many applications, electrical, computer, and many other engineerings and sciences, this quantity is viewed as some form of energy. So I put it in quotes because a lot of times in electrical and computer engineering, we're talking about actual physical energy, and sometimes we're talking about things that just behave mathematically like they should be associated with some physical real quantity of energy. So that's why I put the quotes there. And so why do we think of this thing as an energy here? And obviously we're looking at this as a function of the vector x. So is it measuring the energy of that vector x? Well, yeah, it is measuring the energy of the vector x in kind of a general way. And so let's see why we say that. So let's think about the potential energy of a spring, or the potential energy of some mass held up at some height or something like that. So for the potential energy of a spring, the further you pull it, the more potential energy there is. But it turns out that the amount of potential energy goes up as the square. So if you double the displacement of the spring, you've actually quadrupled the amount of energy that you have the potential of releasing when you let go of that spring. And all this stuff out in front, just some constants. 1/2 and k, they're just some special constants, spring constant. If we do a mass at some height, we'd have 1/2 mx squared. So energy involves squares of things, and you can see this quadratic form here, and we'll use that term more generally. So this is a quadratic function, very simple one. It's just a plot of this. Now, there are lots of energies that involve squares. So we talked about the potential energy up here of springs and masses at specific heights, but we also have kinetic energy, which has to do with the square of a velocity. And again, here's some constants out in front. In this case, it's half the mass. If you've started to study circuit theory, and you probably learned this in a physics class as well, if you have a capacitor, so that's why I have cap here. If you have a capacitor that has a voltage V on it, the amount of energy stored in that capacitor, and that's one of the things that capacitors do, is they store energy. So the amount of energy stored in that capacitor is proportional. Here's our proportionality constant here. I didn't change my M. That should be capital C. I'll have to go fix that. But the important thing is not the constant out in front, at least for what we're talking about. It's that it's related to the square of the voltage. And then we've got a resistor. So we can find the power dissipated by a resistor with a resistance value of R is I squared times R. Now, technically this is a power, but power is related to energy. Do you remember how? Well, if you're an electrical or a computer engineer, that's something that you should be aware of. So these are things that we shouldn't just learn and forget. We're building a structure inside your brain to help you think like an engineer. These are things that you need to have at your recall. These are not things to be crammed into your brain for an exam and then disposed of after that exam is over. This is what will make you a good engineer. That's why I teach the way that I teach, trying to touch back to fundamental ideas. Power is the rate at which energy is either being delivered or dissipated. So if we think about a time rate of change of energy, that gives us power. So anyway, the energy, we can't really talk about the energy stored in a resistor because energy isn't stored in a resistor. But as we pump current through this resistor, the rate at which energy is being dissipated depends upon the square of the current through it. And then we have the famous one, E is equal to mc squared. Why we don't have a half there, I don't know. You'll have to ask Einstein that. I'm not a physicist, so I can't answer that one. But there we should have the m, that's the mass. And c here is the speed of light. So it's kind of like this one, but not exactly. Very, very different. So squares, energy is focused on squares. And so let's look at this form that we're talking about here, x transpose AX. We call that form a quadratic form, regardless of the fact whether A is positive definite or not. Now obviously A has to be square in order for this quadratic form to work. You can figure out that that must be true. But we have a quadratic form. It's just a name we give it to it. Why do we give that name? Well, form, it's a form. Formula, short for formula perhaps, but it's not a formula because there's not an equal sign here. It's just a form. Okay, but why do we say it's quadratic? Let's take a look at it. And why should we view this quadratic thing, this thing that we call a quadratic thing, why should we view it as energy? Well, let's take a look. So here's our our x transpose AX. Here's our x transpose. Here's our A, symmetric as it must be, because we could form the quadratic form for any A, but we're interested in positive definite matrices, which we've already established must be some subset of the symmetric matrices. And then we've got our x over here. And if we multiply this all out, so go back to one of those early lectures and you can remember how to do that multiplication to get a 2 by 1 vector, which would then multiply this 1 by 2 vector, and you'll get this scalar, right? This multiplication will give you a 1 by 1. So let's look at this. We've got two terms that involve squares. So it's, and the coefficients on them are the diagonal elements of the matrix. So we've got a diagonal matrix element times the square of one of our variables, the other diagonal matrix element times the square of the other one. And what do we have left? We have 2b x1 x2. So when we do this multiplication, we'll get a bx1 x2 and we'll get a bx2 x1. X1 and x2 are just scalars now, so you can interchange them and then add those two terms together and you get two of them. So notice that this term here will certainly be positive if A is positive, which we've seen needs to be the case for a positive definite. And this term will be positive if C is positive, which we've also seen needs to be the case for a 2 by 2 positive definite matrix. But this term, we say B, we haven't put any constraints on that as far as must be positive. And x1 and x2, well, they can take on individual values, so x1 could be positive while x2 takes on a negative value. So this term here has the potential to be negative. And what we're looking for are matrices with B's relative to A and C such that this middle term can never be so negative for any x vector that we put in that it will make this result go negative. So this result will we're aiming to make it always be greater than 0, something like that. So we call this an energy. Well, we'll be a little loose here. It's got squares in it, so let's call it an energy. Oh, and it's kind of got, it's got another second order term. Not really a square, but it's a second order term. So we should say we call it an energy because it's got second order terms in it. But what about that middle term there? Should we count that as an energy? Well, it turns out that in physics and science and engineering, in many applications, we think of that as kind of like a cross energy. It's kind of a coupling energy between whatever x1 represents and whatever x2 represents. So it's kind of a generalized energy. And that's another idea that I'd like to bring out in these lectures, is the idea that don't get fixated on, well, this is how it is. Broaden your view. Sometimes it'll take you down a road that's very interesting. So maybe we can generalize the idea of energy where it's not just a square, but it's at least something times something else. And it's not a real energy, but it's some sort of cross energy. So the guy who invented imaginary numbers and complex numbers, that's the kind of line that he was thinking about. people were saying there are no roots for these equations. And he said, well, not in the number line we know, but what about another set of numbers? And he invented those. And so here's a new way of thinking about this. Cross-energy terms. And again, we're not going to get into the physical meaning of this, but just accept it for that. So what does this quadratic form look like for a 3 by 3? I know when I went through this as a student, I was thinking it's going to have third order terms, isn't it? But do it out. Work it out. If you work it out, and I would encourage you to do this by hand, these are all the terms you get. These are not three different elements of a 3 by 1 vector. Notice I put a plus sign here, and then I reinforced it over here. And I put a plus sign here, and I reinforced it over here. So there's no way that you're going to miss that all 9 of these terms get added together. So it's a sum of 9 terms. 3 of them are squared terms. So here they are. I couldn't remember if I had highlighted those in some way. And where do they come from? They come from the diagonal elements, A1, A2, A3. And I used a different notation here. I could have just kept it as letters, but I wanted to make it clear which ones were diagonal elements and which ones were off diagonal elements. So the diagonal elements I notated with A's with subscripts so that you can keep track of them. The off diagonal elements are B's and C's and D's, but notice that I enforced the symmetry on those, right? Okay. So let's look at this. What do we got here? Well, we've got these squared terms down the diagonal. So the squared terms are definitely greater than 0. Where'd my ink go? There we go. Squared terms are greater than 0. So we need the diagonal elements to be greater than 0, as we've seen before. So these diagonal elements all need to be greater than 0, and that'll make all those terms greater than 0. And we also get some idea that, remember when x1 and x2 take on values of different sign, this term here can go negative, right? And so B can't be too large. Same thing that we were seeing before. So this equation, even though it's a little harder to say exactly the values that B, C, and D can take and still be positive definite, but for positive definite, these off-diagonal values can't get too big. So if you make them too big, no longer positive definite. So here's our definition. Matrix A is positive definite. This is a new definition. So it's an alternate definition. Matrix A is positive definite if its quadratic form is greater than 0 for every non-zero vector x. Obviously, I can make this thing equal 0 if I pick x equal to 0, but I don't want that, right? So this has to be greater than 0 for any non-zero vector x. Beautiful. Okay. So we already showed that if the eigenvalues are positive, then this is true for each eigenvector. But now we're saying it must be true for every non-zero vector x. That's what we're saying here. Must hold. So the way that most people define positive definite is this way. And then they argue that that then shows that the eigenvalues must be 0. Or I'm sorry, greater than 0. So as I said, this is the more fundamental definition of positive definite. And then we show that the positive definiteness under this definition implies positive eigenvalues. So we're not going to do all that proving, but it could be done. So let's look at a nice ramification of this energy-based view of positive definiteness. So we can immediately use this energy-based view to say if A is positive definite and B is positive definite, so is their sum. And we can easily verify that. We take A plus B. So we're aiming to show that this thing here must be greater than 0. We just pass these through. So we pass the x transpose into there and the x into there, x transpose into there, x into there, and we get these two terms. But because they're each individually positive definite, this is greater than 0, this is greater than 0, and so the whole thing must be greater than 0. So it's difficult to keep track of pivots and eigenvalues when you add matrices together. It's a tricky problem. I've had projects that I've worked on in my research where I have two separate matrices. I know that they're both, I know the eigenvalues and eigenvectors of each of them, and then I end up with a sum of them, and I'd really like to be able to relate the eigenvectors of the sum to the eigenvectors of the individual ones, but there's just no easy relationship. But if all we want to know about are the amounts of energies, so these energies add, so that's a nice result. It didn't help me in that research project, but it does help in other areas. So this quadratic form in this new way of defining positive definiteness connects with our final way to recognize a positive definite matrix. So if the columns of some rectangular matrix R are independent vectors, then if we form a matrix by taking R transpose times R, and notice we're allowing a rectangular matrix here. It could be square, because obviously squares are rectangles, but we can let it be rectangular because the product of this will give us a square matrix. So this is a really nice result, and this shows up all over the place. So another way of saying this, and this is the way that I prefer to say it, it's really saying the same thing with just slightly different wording. Matrix A, so here I'm starting with R and I'm forming A and saying that the result is positive definite. Here I'm starting with A and I'm saying that matrix is positive definite if and only if I can split it into some matrix R and take R transpose times R, and that R can be possibly rectangular, but the R has to have independent columns. So again, this idea shows up all over the place. So just summarizing the 5 different ways that we've seen to test for positive definiteness or positive eigenvalues. So when a symmetric matrix has any one of these 5 properties, it has them all. So these kinds of results are extremely powerful. It means you show, I've got a matrix that has this one thing, boom, you suddenly have 4 additional characteristics of that you've established. So all n pivots are positive. All n upper left determinants are positive. If you remember, we talked about taking the upper left element, then the upper left 2 by 2, then the upper left 3 by 3 to find whether a 3 by 3 was positive definite. This is generalizing that idea. All n eigenvalues are positive. The energy is greater than 0, except for x is equal to 0. And then we can factor A into some R transpose R for some rectangular matrix R with independent columns. So when we talk about these upper left determinants here, we just have a little footnote down here that says the upper left determinants are 1 by 1, 2 by 2, all the way up to n by 1, or I'm sorry, n by n. And that last one is the determinant of the complete matrix A. So remember, those determinants always have the upper left element in them. That's kind of the anchor point. So that's a beautiful result. Show that you got any one of those things and you automatically have the other 4 of them. So here's an example. Here's a matrix A. We've seen this matrix over and over again. Let's test for positive definiteness by applying all 5 tests. Okay, the first one. I don't go through the intermediate results, but we've seen how to find the pivots of this. Do row reduction, find your pivots. You'll find the pivots are 2, 3/2, and 4/3, and those are all positive. So bingo, positive definite. Number 2, check its upper left determinants. So there will be 3 of them. So the upper left determinant, 1 by 1 is 2. Do the upper left determinant of the 2 by 2. So we're going to have 4 minus 1. So that's 3. And then, well, if we did our little trick of extending the columns over here and doing the diagonals this way, if you did all that, you'd find out that the determinant of it is 4. And those are all positive. Bing! Positive definite. We could calculate, sorry there, got tangled on my tongue. We could actually calculate the eigenvalues, and we would find out that they are 2 minus square root of 2, 2, and 2 plus square root of 2. Look at that beautiful symmetry. This is what gets mathematicians all excited when they see things like this. Well, it gets me excited too. I look at that and go, that's so cool. It's like when I was, I don't know, 8, maybe, handheld electronic calculators were just becoming available for reasonable amounts of money. And my brother-in-law, my sister's much older than me, my brother-in-law gave me one of these things, and I was playing around with it, and I discovered that if you took 0.222222 times 0.5555555 to some number of digits there, on that particular calculator, you would get 0.1234567 Later, I figured out why that works. It's cool. Try it. See if you can figure out why. I also figured out that if you have more digits on your calculator, you'll see it go 0.12345678987654321. You have to choose the number of digits just right. Try it in MATLAB. Set to show a large number of digits, format long, and then play around with different lengths of 0.222222 and 0.5555555. Play around with it. Then see if you can prove why that works. Anyway, cool results here. 2 minus square root of 2 and 2 plus square root of 2. These two are obviously positive. That one, well, yeah, square root of 2 has to be less than 2. So, yes. And we can show that x transpose AX is greater than 0. So we can do that here. Requires a little bit of tricky algebra to do this. There are other ways to do this, but all we're doing is just regrouping terms so that we get a bunch of terms, all of which are squared with positive constants out in front. And it's no accident that those numbers are the pivots out in front. Coolness, huh? This matrix has a lot of cool things about it. So we showed that, and then the last one is we have to show how to factor A into R transpose R, where the columns of R are independent. And actually we can do this 2 ways. And there may be more than 2 ways, and in more general settings there may be many ways that you can do this, but there may be times perhaps, I don't know for sure, but I'm not going to say that there aren't, cases where you've got an A and there's going to be only one way that you can factor it this way so that it will work. But in this case, I'm going to show you at least 2 ways. So we've seen this factorization before when we've played around with this matrix, but you can verify that when you multiply these 2 matrices, you get our given matrix. And so look back in the notes. We saw this factorization before. I can't remember exactly where. And it's pretty clear that R has independent columns, since each new column hits a new dimension that the previous columns had not covered. So that's pretty clear. And here's another way. So if we do our symmetric version of the LU decomposition, so think way back to when we talked about that. For the symmetric version of LU, we get an L and an L transpose, and we can pull out a diagonal matrix in the middle. And for this matrix, here's the L transpose, and the diagonal matrix that we get in the middle, notice all non-zero values. And notice pivots. Those are the pivot values that we saw. So we've seen this decomposition before as well. And then we can split D, so this middle matrix here, where's my pointer? This middle matrix here is D, so we can split D into something called the square root of D times the square root of D. And why can we do that? Well, all we got to do is take the square root of each of these numbers, and we can do that because none of them are negative. If we took a square root, otherwise we would end up with things that are complex, and that would kind of ruin what we're trying to do here. So now we can write, we can take this D, split it into this, and actually, well, D will be symmetric, so we can actually do this as D transpose, and that's how we end up with this over here as a transpose. And that's we'll define that to be our R transpose R. So this is our R, and this is our R transpose. I know that it seems odd to call something with a transpose on it R, but we can. So there's our two ways to split that. And we know that the columns of the L matrix are independent from each other. So we've been talking about positive definite matrices where that quadratic form can never go to 0 except when x is equal to 0. But no, and that also told us that the eigenvalues were all strictly positive. None of them could be 0. Certainly none of them can be negative, but none of them could be 0. Let's talk about semi-definite matrices. What we're going to do is allow the smallest eigenvalue to become 0. All the other ones will be positive, so they'll be above that and bigger than that. And there may be more than one eigenvalue that's 0. Remember, we can have repeated roots for a polynomial. We can have repeated eigenvalues because they come from a polynomial. And all that means is that there's going to be, if there's two eigenvalues that are 0, it just means there's got to be two eigenvectors corresponding to that. And since we're talking about symmetric matrices here, those eigenvectors will be orthonormal to each other, orthogonal. So we'll call such a matrix positive semi-definite. And what that means is there is at least one, but there's going, obviously going to be more of them, one non-zero vector for which this is true. X is equal, the quadratic form is equal to 0 for non-zero vectors. So for positive semi-definite matrices, this is our usual definition, the second column or the second row here. And the result that we usually drive towards once we have that definition is that some of the eigenvalues will be equal to 0. If they were all non-zero, all greater than 0, technically it would satisfy this, but we wouldn't call it positive semi-definite. We would call it positive definite. So you have to have at least one 0-valued eigenvalue. So interesting thing here, pointing out as we go along here. So positive definite matrices are invertible, and that's a nice property to know. So if we have A, we know that we can split it into eigenvector decomposition. So Q is a orthogonal matrix with the orthonormal eigenvectors in it as columns. Lambda here is a diagonal matrix with the eigenvalues down the diagonal. So there's zeros all out here and zeros all out here. But all of these eigenvalues are greater than 0. And you can verify, we've mentioned this before, that the inverse of A will just be Q times the inverse of the diagonal matrix times Q transpose. And we know that the inverse of a diagonal matrix requires all the eigenvalue or all the diagonal values to be non-zero, and we have them all greater than 0, so that satisfies. So we can just take the reciprocals of them. And notice that all of those are positive as well. So I didn't state that here, but if A is positive definite, then so is its inverse. Its inverse exists, and so is its inverse is also positive definite. Now things are not quite so good as far as inversion for positive semi-definite. So positive semi-definite matrices are not invertible. That's because at least one of these numbers is equal to 0. So when we try to form the inverse, we need these reciprocals. And when we take 1 over 0 for that 1 0 term, things go wrong. We can't evaluate 1 over 0, so the inverse does not exist. So that's an important distinction between positive definite and positive semi-definite. So in a lot of applications, we set things up and we say, well, gee, everything's telling us that we could have at least positive semi-definite, but we might have positive definite. And we might have to work hard to show that the matrix we're playing with is actually positive definite so that we can do the inverse of it. Because we might need that in our algorithm for doing cellular communications and things like that. So you think I'm kidding. No, these things are done inside cell base stations all the time as ways of, you look up at that cellular base station and it's got a bunch of antennas there. You might wonder, what are they using all those antennas for? They're forming a very complicated antenna processing system from that. And a lot of the algorithms that do that are striving to do it optimally. And if you write down all the mathematics for this, guess what pops out of these things? Positive definite matrices that need to be inverted, or at least matrices that need to be inverted. And then you can show if you configure your antennas this way, bang, it becomes positive definite, and it's invertible, and everything will work, and you'll get praise from your boss and your coworkers, and you'll publish a paper, and maybe your algorithm will lead to a patent, and you'll end up being famous within a very small group of people, but famous nonetheless. So yes, these things show up inside cell phones, or more likely cell phone base stations, and all over the place. Okay, I love this idea. It's pretty cool. You would never guess that suddenly from positive definite matrices we're going to end up talking about ellipses. And you might wonder why this shows up in electrical and computer engineering. But what have I been telling you? Yes, it does. It does show up in the most unlikely places. So if you've got positive definite matrix A, and you find the set of all vectors such that for some k greater than 0, we have the following. So in other words, we're setting an equation now. We're saying, for positive definite, we know that this thing will always be greater than or equal to 0 for every x that's not equal to 0. But now we're looking for all the x's that when we plug them in here. So I pick an x, I plug it in both of those places. Does it equal k? No, then it's not in this set. Pick another one, plug it in. Does it equal k? Yes, it's in this set of vectors that we're looking for. Keep doing that. Find all the vectors that satisfy this equation. Guess what they look like? They look like an ellipse. Well, for 2D, that's easy to see. Do this multiplication out for a two-dimensional matrix where A is symmetric, and now I've switched to a different scheme here, which is a little more obvious. A11, A22 are the values in A down the diagonal. This is just our standard matrix indexing scheme. And then since A is positive definite, it is symmetric. So A12 and A21 are equal to each other. So I just wrote both of those terms in terms of A12. And if you go back to your calculus book or maybe your analytic geometry book, or, all right, just Google it. Because you probably don't have books anymore. You just Google everything. Look wherever you look for math ideas. You'll find that you have seen this equation before when you talked about the equation for an ellipse. And here's a nice picture of an ellipse. So every point on this ellipse, so if I pick this point right here, and I put in that x1 value and that x2 value into this equation, it'll be equal to the value of k, whatever I set k to be. If I set k to be a little bit bigger, it'll give me the same orientation ellipse, just a little bit bigger. I set k a little bit smaller, it'll give me the same orientation ellipse, just a little bit smaller. Okay, so k is not terribly important. But what's important is the orientation of the ellipse. And that's set by the A11, the A22, and the A12. If you remember when you talked about ellipses in analytic geometry, you talked about how sometimes they were aligned with the axes and sometimes they weren't. All right, cool. So we've now tied this back to matrices and vectors and quadratic forms and positive definite matrices. And what would all this stuff look like in higher dimensions? Well, in 3 dimensions, we would have a 3-dimensional ellipsoid. So I just drew 2 of them here using MATLAB, and I'm just showing them both at the same time. So it's not like we get 2 of these from one equation. So this part here is one ellipsoid, and then this part here is a second ellipsoid. So I just showed 2 of them. And in higher dimensions, 4 dimensions, well, you can't draw it, but it's going to be a 4-dimensional ellipsoid, a 5-dimensional ellipsoid, a 50-dimensional ellipsoid. I don't know what that's going to look like, but you can sort of, no, you can't really visualize it. But you can visualize a 3-dimensional one. So how do the matrix elements impact the ellipse? If I wanted to make one that was tilted a certain way, how would I set up my A matrix to do that? Well, one thing we know from our early studies of ellipses is that if this term is 0, so this term goes completely away, we know then that the ellipse is aligned with the axes. So this ellipse now would, maybe be like this, or it would be like this. And we also know that it's the relative values of A11 and A22 then, when this term is gone, that will set which axis it's biggest along. Okay? So we know that. We remember that. So a diagonal positive definite matrix will not have any of these cross terms. So it will give an ellipse that is aligned with the axes, or an ellipsoid in higher dimensions. So here's the amazing part, even more amazing. The eigenstructure of the matrix tells us an awful lot about the ellipse, and that's a really cool way to look at an ellipse. So you may have learned the term principal axes of the ellipse. So you draw, we'll imagine the ellipse being centered at the origin. Where's my pointer? I have to draw with it. There we go. So if I draw a vector out to that point there, and this is a tangent line, so I'm going to draw it out to the point where the tangent line is orthogonal to the vector. Here's another one, so there will be 2 of them. Those are the principal axes of the ellipse. And I think there are some other terms for that, but that's the name that I know for them, principal axes. And they are orthogonal to each other. And they're orthogonal to the tangent line. So let me illustrate what happens when we pick some other vector. So if I pick some other vector and let me just go along the axis here. I go out to this point. Well, the tangent line is here. that certainly is not a right angle, right? So the only place that the tangent line is orthogonal to the vector is at, well, the points that are kind of the obvious edges or endpoints of the ellipse. Those are the principal axes. They're orthogonal to each other. Ellipses come from positive definite matrices that have orthogonal eigenvectors. So here's this discovery thing, this I wonder if kind of thinking. I wonder if, or I wonder, could these principal axes, since they're orthogonal, could they actually be the orthogonal eigenvectors of this matrix? You bet, they are. And here's the theorem. The principal axes of the ellipsoid, defined this way through this positive definite quadratic form set equal to some positive number k. K has to be greater than 0. I guess I didn't say that earlier. Are eigenvectors of the positive definite matrix A. Now to prove that, we could use some ideas from Calc 3. There may be some other ways to do it that doesn't involve Calc 3 and might be more just linear algebra-ish that I could present here, but it wasn't clear to me. I don't know how to do that. This is the way I know how to do this is using Calc 3 ideas. So chances are you've not had Calc 3 yet, so we're not going to do that. So what we're saying is that when x is picked as one of the principal axes, when we multiply a times x, it just grows it a little bit longer or a little bit shorter, but it keeps it in the same direction. It's in exactly the same direction. That's pretty cool. And it's even cooler that we can actually prove that that is true. And likewise, if we picked one over here, that would be the other eigenvector. That also would, AX would lie along it. It wouldn't flip because remember, positive definite eigenvalues are positive. But what we can prove is this little second part of this theorem. So really these are one theorem, usually presented as one theorem. The principal axes of the ellipsoid are the eigenvectors, and the lengths of the principal axes are given by this formula, which involves the eigenvalues. So the principal axis associated with eigenvalue lambda sub I is square root of k over lambda sub I. So as I increase k, the size of the ellipse will get bigger because that's telling me that the principal axis now will be out a little bit farther. And we can see how much farther. If I quadruple k, I'm going to double the size of this because of the square root. But how are they related to the eigenvalues? Reciprocally. Well, square root reciprocally. So if I increase the eigenvalue, the size of the ellipse will go down. So what that tells us is that the small eigenvalue has the large distance and the larger eigenvalue has the smaller distance. Interesting. Let's prove this idea. Very, very easy to prove, like a 1-2 line proof. So if x is a principal axis from the result up above that we did not prove, then we know that ax is equal to lambda x. And here's that same step that we're always doing. Take the inner product of such and such with such and such. So take the inner product of both sides with, should be x transpose. So I'll try to fix that in the notes, but if I don't, pencil it into your notes. Now we get this on the left, we get this on the right, but we know that from our definition of the ellipsoid, everything on the left now must be equal to k. So we have k, a number, is equal to lambda times the norm squared of x. So the norm squared of x, and remember, we picked x to have the length that takes it out exactly to the edge of the ellipsoid. So the length of that, just solving for that, length squared is k over lambda. We need to get rid of the square, so take the square root. So the length of x, the length of the principal axis is this amount. So that's remarkable. So the ellipse is tilted when the eigenvectors are tilted with respect to the axes. If you pick a matrix with, if you want an ellipse to be tilted a certain way, you can create that matrix. Pick your eigenvectors to be tilted the way that you want. You want it to be long along this, short along this. Pick your eigenvalues that way. So you can then pick the smaller eigenvalue to give the longer principal axis and so on. So if the matrix turns out to be positive semi-definite, what happens? One of these is going to be 0. At least one of these is going to be 0. And so the length of one of the principal axes goes to infinity. Well, what would an ellipse in 2D look like with one eigenvalue that's not 0 and one eigenvalue that's 0? Well, here's our axes. What would it look like? Well, with two non-zero eigenvalues, it looks like this. It looks like an ellipse. Now imagine drawing two parallel lines, straight lines. I'll draw them the best that I can. So this goes on to infinity. That's the length of an infinitely long principal axis. It's a degenerate case. It's not really what we would consider a true ellipse. So you got to keep your eye on that case when you're trying to work these things with ellipses. All right, I think we're getting pretty close to the end here. This might be the last slide. Yes, this is the last slide. So this eigendecomposition, if we think about what it's doing, we've talked about how it diagonalizes a matrix. If we were to multiply by Q transpose over here and Q over here, we would get rid of these things and we would have diagonalized it to lambda. So if we plug in for A, let me clear all this stuff off. If we plug in this eigendecomposition for A, we plug that in here. Now it's sitting right there. And now we're just going to group things. We're going to say that, oh, this is X, so this is all X transpose, but we'll call it capital X now, just to distinguish it. I could have used something else like an X tilde or X hat or something like that. But here's a new quadratic form in a new set of axes, not corresponding to little x, but corresponding to big X. And since it's a diagonal matrix in this new coordinate system, my ellipse is aligned. So Q is an orthogonal matrix. So what it's doing here, remember, rotations were orthogonal matrices. That's all this is really doing, is rotating in maybe in a slightly more general way than just simple rotation, but rotation to align the new axes with the ellipse. And we could draw a nice picture of that, but I didn't do that here. I think the book might actually have a picture of that, so you can check that out. All right, I'm going to stop here, and that's our end of our discussion on positive definite and positive semi-definite matrices with amazing connections to ellipses, and hopefully I'm encouraging you to think like an engineer, think like a researcher, think like a scientist, and say, I wonder. So that idea of discovery, seeing something and then trying to push it and establish that, yes, my hunch was true. Well, sometimes it turns out your hunch isn't true, but chances are if you follow a hunch that's not true, you'll discover something else kind of interesting along the way. All right, we'll see you in the next video.